Isaac Newton studied physics and the effects that it had on the world. Newton created 3 laws explaining several rules concerning the laws of motion and the forces that are applied when an object interacts with another object. Newton's first law states that an object in motion stays in motion, and an object at rest stays at rest unless acted on by an outside force. His second law states that the acceleration of an object is directly proportional to the force and inversely proportional to the mass. His third law states that for every action there is an equal and opposite reaction. We created mousetrap-powered cars during the second quarter. Our goal was to make the car travel a total of 45 tiles down the hallway with a deviation of 1 tile or less. We had to accomplish this in as short a time as possible. Each tile was 30.5 centimeters long, so our car needed to travel a total of 13.73 meters while traveling as straight as possible. We spent several weeks working on this project, and we eventually accomplished our goal.
We created the mousetrap-powered car in order to apply Newton's laws to real life and to show how they affect us in our everyday life. We used Newton's laws in order to make the car travel straighter and faster, as well as travel for longer distances. We learned that the car would keep moving as long as no outside force acted on it. Since eliminating friction was impossible, we tried to make it so that it affected the car as little as possible. The less friction acting on the car, the longer our car would travel. We also learned that the acceleration of the car changed depending on the mass of the car and the force of the lever arm. We needed to keep the car as light as possible and create as large of a force as we could with the lever arm. As our car increased in mass, its speed decreased, so therefore we needed to modify the car in such a way that it affected the mass as little as possible. We used Newton's third law when we decided the degree to angle the car. We angled the car so that when the car hit the wall, the force that the wall applied back at the car caused the car to ricochet and continue down the hallway. The force that the wall applies to the car is equal to the force that the car hits with, so we do not want to hit the wall with a lot of force because it could damage the car.
Newton created 3 laws regarding the laws of physics. His first law states that an object in motion will stay in motion, moving at a constant speed in a constant direction, and an object at rest will stay at rest unless acted on by an outside force. This means that an object will not change its state of motion unless another force acts on it. One example of this is a car that continues to move at the same speed unless it is stopped by an outside force. Normally this force is friction. Our mousetrap car continues to move in the same direction unless it is acted on by another force. Friction will always act on the car, slowing it down and eventually stopping it. If we reduce the friction acting on the car as much as possible, then the car will travel farther than before. We reduce the friction by applying graphite to the axles and preventing the wheels from rubbing against the body of the car. Another example is when a car collides with a wall. It comes to rest, but if the force of the wall is not great enough to stop the car will keep moving. The outside force acting on an object must be able to overcome the net force that is already acting on the car. If we angle the car, then the force of the wall on the car will not be great enough to stop the car, and therefore the car will continue to move. This means that we do not want to collide with the wall head-on. Instead, we need to hit it at an angle. A final example of this is a car moving at a constant speed and a constant direction. Our car continues to move at a constant speed and direction if we align the wheels so that they are straight. We have to prevent the wheels from wobbling because wobbling wheels will produce a force that causes the car to shift to either side of the hallway and we will not reach our target distance.
Newton's second law states that the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of the object. This can be simplified into the equations F equals ma, A equals F over m, or m equals F over a. This means that the force on an object is equal to the object's mass multiplied by its acceleration. For our first example, the force of a mousetrap car when it is moving is equal to its mass multiplied by its acceleration. If the mass of the car is 1 kilogram and the car's acceleration is 0.5 meters per second squared, then the force of the car moving is 0.5 newtons. If the mass were greater, like if we added some weights to it, then the force of the car would be greater. For our second example, the acceleration of the car is equal to the net force acting on the car divided by the total mass of the car. We use this formula to calculate our car's acceleration, and this allowed us to predict how far our car would travel. The greater the force, the greater the acceleration, and the greater the mass, the smaller the acceleration. For our third example, the mass of a car is equal to the net force acting on the car divided by the acceleration of the car. We use this in order to calculate our car's mass. We used the formula to make sure that the mass of the car did not get too great, because this would slow down the car. The greater the mass, the greater the force, but an object with a lot of mass would have a small acceleration.
Newton's third law of motion states that for every action, there is an equal and opposite reaction. This means that if a force acts on an object, there is a reaction force acting against it. This is why when someone is standing, they do not push the ground away beneath their feet. The ground pushes back on them, and the result is that the person is stationary. However, the reaction force can act in a different way than the force, allowing the object to move. One example of this is if a car were to hit a wall, the wall would produce a force as well as make the car bounce off. The wall essentially hits the car, as the car hits the wall. The wall can withstand the force of the car, however, cannot, and the car gets wrecked. Another example of this is if a car is driving down the road pushes on the wheels as the wheels push on the ground. The wheels try to push the road backwards, the road pushes back on the wheels. Since the road isn't going to move, it is the car that is pushed forward. This is how a car moves. A final example of this is when the car moves, friction acts against the car's movement. The force of the car moving has friction acting against it. This can be in the form of air resistance or friction from the ground. It opposes the motion of the car, and therefore the car's acceleration is slower.
In conclusion, Newton's three laws of motion apply to the cart in various ways. Every moving part on the mousetrap car can be broken down into various ways Newton's laws affect them. Newton's first law affects the car because the car keeps moving until an outside force affects it, which in this case would be the wall that collides with it in the end. Newton's second law applies because the car's force is equal to its mass multiplied by its acceleration. Newton's third law applies because every moving part of the mousetrap car, and even the car itself, has action-reaction forces upon it. The lever arm, the wheels, the spring, even the car itself is affected by them. These forces both help and hurt the car, but there is no way around them, so we have to work with them. Newton's laws affect us daily, and our mousetrap car demonstrated them in action.